Welcome back, everyone. Continuing our problems, our example problems on kinematics and applying our 5 equations of kinematics. This is example 2,4D. If you just watched the last one on 2,4B, you may be asking yourselves, why do we skip question C? Well, there were some issues with that I need to fix, so we're just going to go ahead and skip that one. So we have a train, a 90-meter long train accelerating uniformly from rest. Okay, so constant acceleration. Initial velocity is 0, at least initially. And the front of the train has a speed of 20 meters per second when it passes a railway worker who is standing 180 meters from the front of where the train started. Wow, okay, what's going on with that? Well, let's go ahead and just start drawing some little free body diagrams right here. I'm going to squish this down and put this kind of up in the corner like that so that we can have a little more space to draw a free body diagram. But I'm going to draw at least our first diagram right in this little box right here. Okay. So here's our railway worker right there. Our train, which I'm going to make black, is way down here. So there's the train engine and all the cars. All right. And it's moving towards the railway worker. The train is 90 meters long. Okay. From there to there. And this distance right here, this displacement that it moves towards the worker with, is 180 meters from there to there. So the question is, at least the first question, when it finally reaches the railway worker, so he's right here, it's we're going to assume it's next to him. It's not in front of him, so it's not about to run him over. You know what? I should make it a little bit closer to him. So it finally reaches him right there. Okay. Those are the cars and the train and everything like that. What is the velocity? I believe that's what it's asking right there. No, I'm sorry. How long did it take for the front of the train to reach the worker? That's what it's asking us. In fact, we know the velocity. This final velocity right here, when it reaches the worker, is 20 meters per second. All right. Initial velocity right here, we know that to be 0. It starts from rest, right? It accelerates uniformly. We don't know the rate of acceleration, but it is a constant acceleration. We're solving for time. All right. So how long does that take to solve for the train to reach where the worker is standing? Okay. Well, I'm going to start that in red up at the top. In fact, I'm going to call this part A right here. That's going to be part A. Let's write down our knowns. We know our initial velocity equals 0 meters per second. What else do we know? We know our final velocity, V final, equals 20 meters per second. The distance that the train displaces, now that is, we might say the front of the train displaces from 180 meters, it displaces itself 180 meters to reach the worker. So that's our displacement, 180 meters, okay? And we're solving for time. Time, we don't know. We also don't know the acceleration either, but we can actually find that out. In fact, we might just need that for the second part of the problem. So we will solve for that, but we need to find time first, okay? How long did it take for the front of the train to reach the worker? All right, so to get from here to here, how long did that take? All right, well, let's see if we have an equation that has initial velocity, final velocity, displacement, and time in it. We'll go back to our kinematics equations, and I think we do. I think this one right here that I already had circled from before is one that will work. Now remember, this initial position can be subtracted over here, and so it would be final position minus initial, and that gives us delta x. So you can really kind of just bring that over and write it as delta x. Change in displacement equals all this stuff over here. Okay? So it's basically saying displacement is the average velocity times time. So we can say that displacement, here's our equation, equals 1/2 v initial plus v final times time. Now we're solving for time, so we want to get everything else away from it. So what are we going to do? Well, this 2 in the denominator is going to be multiplied up and into the numerator over here. And then the v initial and v final in brackets is going to be multiplied or divided down, so it comes down into the denominator on that side right there. So it's going to look like this. 2 times our displacement is going to be over v initial plus v final. That's going to be equal to t. All right? Let's solve for t. T equals what? T is going to be equal to 2 times our displacement, 180 meters, divided by v initial plus v final. Well, v initial is 0, plus v final, it's 20 meters per second. So what's that? 360 divided by 20? That should be 18, I think. And yes, 18, what? 18 seconds. That's going to be our answer to part A. How many seconds it took for the train to reach the worker. Now, having done this problem ahead of time, I know that there's something else we might want to know for the next part of the problem, and that is the acceleration. All right? We're told that the acceleration is constant. It's a uniform acceleration, but we're not told what it is. We can either come back later and do it, or do it right now. I always like to try to find as many knowns as I possibly can when I do problems. So let's find the acceleration. How long or what rate of change of speed did it take for the train to reach the worker? And it's going to be a uniform acceleration even after it passes the worker. All right? So what is the I'll write this in green. How's that? In dark green right here because I'll have it. Oh, what do I got to do just to get a decent color? There we go. All right, so acceleration equals what right there? Well, now let's assume that we got this right. We've got a time, and we have displacement, and we have initial velocity and final velocity. Well, we can pick from a number of different problems, or a number of different kinematics equations to solve for acceleration. Go with this top one right here. V final equals V initial plus acceleration times time. All right. Now that we have time, we know everything else. Well, we don't know everything else. We don't know, but we can solve for that. So we can say that V final equals V initial plus acceleration times time. Let's solve for acceleration. That means we're going to subtract the V initial over, right? V final minus V initial. And then we're going to have to divide by time. That's going to equal our acceleration of the train. That's going to be what? Well, that's going to be 20 meters per second minus 0 meters per second, our initial velocity, divided by 18 seconds. So 20 minus 0, 20 divided by 18, what is that? I get 1.11 what? Meters per second squared. All right, let's dotted line box that. I usually do that when it's not a final answer, but it's an important thing, an important key to finding out the rest of the problem. Okay? So the rest of the problem, part B, I'm going to call it, is what was the speed of the last car when it passes the worker? All right, so what's happened here is this. We have our dock right here, our loading dock. Here's the worker, and we're picking up where we left off before. So we've got the train that has just started to, there's a smokestack right there. All right, all the different cars, which has just reached the worker, and it's moving that way past the worker. And so then it is now past the worker right here. And I'll draw the worker in brown again. So the train is completely past the worker as he stands on the dock right there. Okay? So what we want to find is the final velocity of the train right here when it's done passing the worker. So what is the speed of the last car when it passes the worker? All right. Well, let's ask ourselves, what was the speed of the car when it first contacted the worker? I shouldn't say contacted, when it first passed the worker. We were told that from the very outset, right? 20 meters per second when it passes the railway worker. It's 20 meters per second. All right. What's the other thing we know about the train? We know that the train is 90 meters in length. So that's the displacement that takes place. So let's start writing these things down. Our displacement, the train displaces itself 90 meters. All right, the initial velocity equals 20 meters per second. Final velocity, we don't know, we're solving for. We need one more known. We need one more known, one more given. Can't plug time in because time to reach the railway worker is going to be different from the time for the train to pass the railway worker, so we can't put in 18 seconds. But we can use acceleration because we just solved for that using the givens from part 1. All right, so, wow, the bell just rang. We're in 6th period right now. Let's just finish this up and then we'll get rolling. Acceleration is going to be 1.11 meters per second squared. We've got displacement. We've got displacement. We've got the announcements on in the background too. Sorry about that. Initial velocity, final velocity, and acceleration. I think we have an equation for that. That is v final squared equals v initial squared plus 2 times our acceleration times our displacement. So let's just solve for v final. That means it's going to be the square root of everything else plus 2 times a times our delta x. And I'm going to let you plug and chug and get your final answer for v final. Okay? So, sorry about the announcement, sorry about the bell, but that's just what happens sometimes. Hope that helps. Let me know if you have any questions, and I'll be glad to talk to you about it. Thanks for watching. I'll see you on the next one.